Hello, my name is Howard Cook. I'm the owner and the founder of Bay Area Retrofit 25 years ago. And I really want to make sure that you understand exactly what you are getting for your money. Retrofits are very expensive and they're also extremely important. You want to make sure it's done right. I really want you to make sure that you know for yourself exactly what you're getting. Some people wonder how it is that I can design their retrofit without actually seeing the house. Now, this has a history. I've always charged, a few $100s to come look at a house. And when I look at the house, say I look at one in Lafayette, and then I go look at one in San Jose, and underneath the house, they all look the same, and the frame would be the same, the bolting would be the same. They all look just the same from underneath. And so what I concluded was they must have been built according to the same building code, and that's in fact what happened. I looked at, say, a house built in say I looked at a house built in 1963, in San Jose, and then I go to Lafayette, and I see one that was built in 1954, and they look pretty much the same. And then I would see that they were both built according to the 1952 Uniform Building Code. So what I would do now is I just look online, I see what the year of construction is, I go look at the building code that was in effect when it was built, and then I can design your retrofit because that building code tells me what the weaknesses were. So that's how I do it. I'm not magical. I can't see through through your house. It's pretty simple. The structural engineer who trained me always taught me that retrofitting is a science. And so the things we're going to do to keep your house from sliding off the foundation are scientific in nature. So I'm going to show you the practice and the science behind what we plan to do to your house. There are two types of retrofits. One applies to houses that have more than 2 steps leading into the front door, and the other one applies to houses that only have 1 or 2 steps that lead into the front door, and that's the type of house you have. If you were to go under your house into the crawl space, this is what it would look like. This is the floor that you walk around on. And then this floor is supported by floor joists. Here's one, that's an important one. It's called an end joist. And then we have a joist here, we have a joist here, and normally we have them every 16 inches all the way down the floor of the house. So that's what supports your house. We want to make sure that that stays on the foundation. So when you jump on your floor, you'll feel some spring, and that's the joists that are springing. And this one right here is especially critical. This one on the end, because if this one on the end goes sliding that way, it'll take the whole house with it, and want to make sure that that does not happen. So what we do in a retrofit is we connect this piece of wood, the end joist, and we connect it to the mud sill, so that this end joist cannot go sliding on top of the mud sill. Now the next thing we do is we make sure that this mud sill is bolted to the foundation right here. Now there's a very, very serious weakness in the building code. And what it says is that there are only 3 nails need to be used to attach the end joist to the sill. You can see it right here in this table right here. Now the reason that's such a problem is because if you look at this joist, and it's 24 feet long, and many of them are, and you only have 3 nails attaching it to the mud sill, it's just not going to be enough. That's a lot of force. Let's say there's 5,000 pounds of force trying to push on 3 nails, and it's not going to make it. So this is the ¡1 thing that we address in any seismic retrofit. And of course we go ahead and bolt it to make sure that there's no sliding there. And that's what a retrofit consists of. So the question is, what do we do about it? This is a very serious deficiency in the building code, and it still exists. So let me show you what happens when these houses are damaged. Let's look at a real house right now. So here you can see this house was bolted. So it's got a nice bolt here, it's got a nice bolt here. They're very close together. But because this end joist right here wasn't attached to the mud sill, and the mud sill runs all the way along here, and then it runs all the way along here, because it's not attached, it just slid right off the mud sill. So that is the big problem, and that's something that we really want to guard against to make sure that you can save your house. So this is what we do. This is an image here of the, there's the end joist, there's the mud sill. We want to make sure they stay together because, as shown here in this arrow, earthquake forces come this way. They push on the end joist, but it's, just sitting there on the mud sill with just a couple nails, so it's going to slide off. So what we do, we install something called shear transfer ties. Those are pieces of metal, and that way when the earthquake force comes this way, that metal has attached the end joist to this mud sill right here, and we end up keeping the floor from sliding off the foundation. This is another case where the fact that the end joist was attached to the mud sill with only 3 nails caused a catastrophic failure. So as the earthquake force went this way and tried to push the end joist off of the mud sill, it just slid right off. If you imagine again, if there's 5,000 pounds of force trying to push push on a house, and there's only 3 nails holding it to to the foundation or to the mud sill, it's going to fail like this every time. So if you were to crawl into your house, this is exactly what you would see. Here's the floor you walk around on. Here is the end joist. Here is the mud sill. And right here is the foundation. It's the exact same thing as you see up here in this drawing. Here's the floor you walk on. Right here is the end joist. This is the mud sill, and this is the foundation. Now what we want to do is make sure that everything remains on top of the foundation so that the floor does not slide off of it. So what we do is we take this end joist right here and we attach it to the mud sill with the shear transfer ties. These shear transfer ties are also called framing anchors. So this is a framing anchor or shear transfer tie. This is a framing anchor or shear transfer tie. And when the earthquake force tries to push the end joist off the mud sill, we keep the two attached with these shear transfer ties. The next thing we need to do is attach the mud sill to the foundation. So this mud sill right here, we want to make sure it doesn't go sliding off the foundation. So we take a piece of steel called a foundation anchor and we attach it to the foundation right here. So here's a photograph of what I'm talking about. So here is the mud sill right in here, and here is the foundation. And we connect the two with this foundation anchor right here. It's bolted here at the top of the foundation anchor, and then it's bolted here into the concrete at the bottom. So what happens is earthquake forces come here, go into the bolts that you see right along this area again, and then that force transfers into the bolts at the bottom, which goes into the concrete. So the way the whole system works is, here's the floor you walk on. Here is the end joist that we saw before. As this joist slides, it goes into this shear transfer tie right here, and this shear transfer tie is connected to the mud sill right here. So that force ends up going into the foundation anchor. This is a typical foundation anchor, and here are lag screws. This is a lag screw, that's a lag screw, that's a lag screw, and there's 5 of them in total. And these lag screws, what they do is they connect the foundation anchor to the mud sill. Now it's really critical that the screws go straight into the mud sill in the center. So they should be about right here. I'd like for you to notice that this one's a little low. The center of the sill is actually right here. This one's, definitely too low. The center is right here. So I'm going to go ahead and show you how you put them in the exact center where they belong. Right now we're going to take a look at a typical foundation anchor and the best way to install it. We don't only install these, there are a couple that we install, but this is the one that is the most common. And they need to be installed in a very particular way, and I'm going to show you exactly how to do that. The first thing we do is make sure that the lag screws go straight in the center of the mud sill as the manufacturer requires. And we do that with a foundation anchor centering tool, and I'm going to show you how we work with that right now. Now we need to get this lag screw right in the center of the sill, or at least it's got to be a minimum of 3/4 of an inch from this edge and 3/4 of an inch from this edge. Now, fortunately, in this case, we have a sill that is 2 inches thick. So what we've done is we put some holes in this jig such that the hole is exactly 1 inch from the top edge of the sill and exactly 1 inch from the bottom of the sill. So when we put this row of holes here, which are pilot holes to guide the screws, if we put them in exactly at these locations, at the spacings that we have right here, when we put in the URFP, the lag screws will go exactly where they need to go. Now, if someplace on your house, we might find a 1.5 inch thick mud sill, because that's some of the Muir ones are that thick. In that case, we use this upper hole right here, because that's exactly 3/4 of an inch from the top. And if we have an 1.5 inch mud sill, it would be exactly 3/4 of an inch from here. And then once you're all done, your lag screws are right in the center where the manufacturer requires them to be. I called the manufacturer Simpson Strong Tie, and he said if you use these particular ones and you don't do this, they will not warrant the product at all. So it's absolutely critical that this is the tested system, and you need to do it the way it was, tested to perform. So now we have a perfectly installed foundation anchor. As you can see here, the screws are straight in the center of the mud sill, exactly where they need to be. So 1 inch from the top, and then we have 1 inch from the bottom. And remember, this is exactly what the manufacturer requires. If you don't do this, you can't be absolutely sure that the retrofit will work, and you'll get the retrofit that your house needs to survive the big earthquake that's coming. Here's another type of foundation anchor we use. It's called an HFA. They don't make them anymore. We just happen to have quite a few, and we do need them quite often. So this works differently. What you do is you put it up against the foundation like that, and then from the top, you end up putting nails like this down into the mud sill. And then you bolt it to the sides like you see there. And these are a really good product. And when we need them, we need them. And we have them in case we need them for your house. In these examples of hardware installation, I was able to stand up, and I did that just so I could, show people how this is done. But in the real world, it looks like this. It's very hard to turn around, very, very difficult to move because of the, just don't have any room. And what I mean by that is that in the real world, when you're trying to install this hardware, it's absolutely critical that the lag screws go into the center or within 3/4 of an inch of the edge of any mud sill. That's the only part that's been tested. It's the only one they know for sure is going to work, and so it's absolutely critical that that then be correctly. So this is an example of one that was not done correctly, and I'll show you how it is. So right here is the concrete. That's the foundation. Right here is the bottom edge of the mud sill. Right here is the top edge of the mud sill. It comes straight across this way, and then this is the thickness, which in this case is 2 inches. So you can see this screw right here is right at the bottom, and this one's really close to the bottom, and then this one's really, so none of these screws are going to work it well. And so as we can see that the manufacturer requires a distance of 3/4 of an inch from the center of the screw to the edge of a sill, center of the screw to the edge. This one, again, it's 2 inches. You could put it right in the center. So this is the sort of thing you really need to watch out for. And if a contractor doesn't know how to do it, building inspectors certainly know not to look for that. They just know, look and see if the thing's up there, and they don't check anything very carefully. Wouldn't even know it's true. So that's why it's so important to make sure this is done properly. When we crawl under a house, we never quite know what we're going to find. In these older houses, before there was a building code, you would find, practically anything. People would come from all different countries. They would, just frame things differently, and you just never knew what you might find. So we've had to come up with lots of engineered systems. Like I said, when I say engineered systems, they've been, well vetted. They've been looked at by structural engineers to make sure that they will work. And so we have to use these fairly frequently, and I'm going to show you one right here. So this is one where we had to put a new mud sill to the side of the foundation. Here's the foundation right along here. Here's a new mud sill, and here's a bolt, and here's a bolt. And we had to attach a piece of plywood right up here, and then we had to staple that plywood directly into the floor. And the way this whole system works is when the floor moves, the plywood will move along with it like this. That transfers into the top of this new mud sill, which is right up here. It's been stapled or nailed in there. And then that transfers the force over to the bolts and into the concrete. So this sort of thing is fairly common. We find this many, many times in practically every house we work on. We carry all the building materials with us. So on your house, we really don't know for sure what type of foundation anchor we're going to use, if we're going to use something like this or something that's even a little bit different. We just never know, but we are prepared under all circumstances to deal with whatever we might find. If your house was built after 1958, it's bolted. The building code required that. Before then, it was kind of hit and miss, but after 1958, you can be assured that it is bolted. However, the building code has changed. If your house was built before July of 2000, then you're going to have a 1/2-inch bolt every 6 feet with little round washers, and now it's changed as of July 2000 that you need a 5/8 bolt every 4 feet with a special type of washer. But even then, the real worry with the existing bolts is that they always have oversized holes. I've never seen a house that did not have this problem, and let me show you what that is. So what happens is the contractor, what they do is they drill a great big hole, much bigger than the bolt itself, before they install the mud sill. This is the mud sill right here. And they do that so they can adjust the piece of wood back and forth, side to side, and that's why they do that. Now the problem is that here's a sample looking down. This is a mud sill with oversized holes. So you can see this bolt is right in the middle, this one's here at the end, then this one's here touching the wood right there. Now the earthquake comes this way. When it pushes against this one first because it's touching the wood, and then it pushes this one, it butts up against the mud sill right here, and then this one isn't doing anything. And then finally what happens, all the holes, they all starting to crack. They're all resisting the earthquake force at that time, and this is the sort of damage that can occur. This is a split mud sill, and this was very, very common in both the Northridge and the Loma Prieta earthquakes, and so that can be avoided. You just rebolt the house. There's no point in trying to fix it. You don't fill the holes with epoxy. You just rebolt the house and it's taken care of. Now the building code only allows a 1/16 of an inch. So if you have anything bigger than 1/16 of an inch, you're into the code violation. And just go take off a nut and a washer and you can find out what you have. Right now we're going to go into the seismic retrofit engineering to design your retrofit to make it as effective as possible. In seismic retrofit work, we don't look at Richter scales. In other words, we're not trying to resist a 7.5 or 7.3. We don't design around that. What we design around is a ground acceleration. So we have an anticipated ground acceleration here in the San Francisco Bay Area of 0.186 Gs. And that's what we need to design against, and I'm going to show you how that's done. So what we have here is the ground acceleration is pushing at the base of the house just like this. So what's happening is the ground is moving this way, and inertia is causing this house to lean, and it's going to want to try to slide off the foundation right here. So in a seismic retrofit, we're trying to prevent that from happening. So I want you to notice how this movement right here, underneath the house, is identical, at least what happens here is identical to a force that is pushing on the house right here. So what we do is we figure out the weight of the house, and we have the ground acceleration underneath the house. And when we multiply those two together, we end up with pounds of force. So we look at, we translate that ground acceleration into pounds of force that are pushing against the house. So all the hardware and plywood and whatever it is that we happen to use in a seismic retrofit is designed to resist a certain number of pounds of force. So we have pounds of force that are pushing against the house, and then we have pounds of resistance provided by the retrofit hardware. So let's see what this understanding of earthquake forces looks like in actual practice. So a foundation anchor can resist 2,000 pounds of earthquake force. And then we'll have shear transfer ties that can resist 1,000 pounds of earthquake force. Now this is only for educational purposes. Foundation anchors, it depends on which ones you use to figure out, how strong they are. Depends on the species of wood. Just depends on the particular foundation anchor. Now the same thing with the shear transfer tie. It depends on the species of wood. It depends on the type, and there are quite a few. So this is just for educational purposes to see how earthquake forces and design principles work when looking at a house. So now we have 10,000 pounds of earthquake force coming in this direction, and we need 5 foundation anchors to total that 10,000 pounds. Then we need 10 shear transfer ties in that same direction to resist 10,000 pounds. Now for 10,000 pounds going in the other direction, it's the exact same thing. We need to have equal resistance on all sides of the house, because you never know how an earthquake is going to attack a house, and the code basically says you need to have equal resistance on all sides, because you don't know, which direction it's coming from. So that's how a retrofit works. We just say a certain amount of force is going to be pushing on the house, and we have foundation anchors and shear transfer ties that can resist the amount of force, and they are rated in terms of how much force they can resist. So now we need to figure out how much earthquake force is going to attack a house, so we can figure out how many foundation anchors and how many shear transfer ties we're going to need. So what we do is we use engineering calculations that are the basis of an engineering guideline called Standard Plan A. I happen to have been on the committee that wrote Standard Plan A, and I have the calculations. I believe I'm the only one who kept a copy of the calculations. I did put them on the web, and you can see them right here behind me as I scroll down them. And so they actually go over the weight of the house. They go, what was was it made out of stucco on the outside, or was it wood? Is it plaster on the inside? Is it sheetrock? Is it 1 story or is it 2 story? What was the year of construction? All sorts of things. They go, what was the roof made out of? They go into all sorts of things throughout how much houses weigh. So we take that number, we multiply it by a ground acceleration, and that was in the 0.186 Gs. And that was a number given to us by a geologist who was on the committee. So we feel very confident that when we figure out how much your house weighs, and then we figure out how much earthquake force is going to attack it, that we can then put in the proper number of shear transfer ties and foundation anchors to protect your house from the anticipated earthquake. Let's see what happens when we apply these engineering calculations to your house. The first thing these calculations tell us is that your house weighs 35 pounds per square foot. Now we take that and we multiply it by the square footage of 1,893 square feet. We end up with this number right here, 66,255 pounds. Now that is how much your house weighs. Now we take that and we multiply it by the ground acceleration that we just looked at. We end up with this number right here, 12,323 pounds of anticipated earthquake force. Now imagine it like this. There's a vehicle and it weighs 12,323 pounds and the bumper is touching the floor of your house. At the same time, it has a chain that's attached to the floor of your house and the bumper. So what happens, it accelerates at 1.86 Gs, then it goes very suddenly in reverse at 1.86 Gs, and it goes backward and forward, backward and forward, backward and forward, the entire duration of the earthquake. And we need to put in enough earthquake resisting hardware to resist that force. Now in your case, what we're doing, we're putting in enough to resist 21,536 pounds of earthquake force, even though we only need to put in enough to resist 12,323. Now we're doing that for a reason. Number one, you're paying us a lot of money and you should get the protection that you're paying for. Number two, if you have earthquake insurance, it's really good to know how resistant your house is, because at this point, frankly, the probability of your collecting on your earthquake insurance is, pretty much zero. And then lastly, I really don't want to get a phone call from you saying, hey, you know what? I really wish you had done more. Our house had a lot of damage. So that's why we really make your house as bulletproof as we possibly can. Now let me show you what these other numbers mean and letters I mean. So anyway, let's say we go to along this foundation here. And what that means is along that particular foundation, we're going to install one foundation anchor, two of the type A connectors that we looked at, or two of the type B connectors, or three of the type C. Now if we come over here and we go to along foundation F, we come down here and we're going to install 8 of the foundation anchors, probably what we saw, 13 of the type A connectors, that's a shear transfer tie, 16 of the type B shear transfer ties, or 19 of the type C shear transfer ties. So if we do this around the entire perimeter of the house, we'll resist the amount of force that we want to resist. Now let me show you what these different numbers are right here. This tells us the capacity of the foundation anchors in old growth redwood. I know by year of construction your house is, your mud sill is old growth redwood. Here are the capacities of the different types of shear transfer ties. If we had to put plywood on the side of the foundation, these are the capacities there. So we know all these capacities, and the people working on your house also know all these capacities. So if some kind of weird thing shows up, they can make sure that when they put all the hardware and the foundation anchors, etc., along a foundation wall, that it resists exactly what it's supposed to be. So let's look at this again. If we install all these different hardware components around the entire perimeter of the foundation, we will resist 21,536 pounds of earthquake force, and your house will be fully retrofitted.